So now let us start with today's class. So today we will discuss singularity, a very important concept concerning complex integration or related to complex singularities.
I'm not able to see where I'm writing.
I am writing that singularities. You are not able to see.
Yeah, no.
Check it.
Yes,
Uh,
sir.
now are you able to see?
Yes, sir.
Okay. Now let us first try to understand what is the meaning of this singularity. So the idea is that a complex function can have a singular point or a singularity, and what it means, we will look at it. So let us suppose I have a complex function f of z. This is a complex function I have. Now the singularity or the singular point, what it is the basically point at which the function is not analytic. So singularity is the point at which the function is not analytic. Point at which the function is not analytic. In a layman term or in a general term, we can say that the point at which the function is not defined. So this trick you can use to find the singularity for a given function. Those points at which the function is not defined, those points will be the singular points.
Okay.
So with this, it will become very easy to understand. For example, I have a function f of z is equal to 1 upon z minus. This is a complex function I have. I know that at z is equal to 1, this function will become not defined. And hence I can say that at z is equal to 1, f of z is not analytic. It's not analytic. Isn't it? And hence z is equal to 1. The singular point for this function is a singular point.
तो ऐसा मतलब हमें ये शो करना है कि जो भी फंक्शन मतलब किस पॉइंट पे एनालिटिक नहीं होगा.
Yeah, that's it. So singular point is that point at which the function is not analytic. But in layman terms, the function is not defined.
Not defined.
Yeah, very easy.
It's upon 0, it's not defined.
1 upon 0 is not defined. And hence z is equal to 1 is the singular point. Now we have different types of singularities. Let us discuss that. Types of singularities. So singularities are the point at which the function is not analytic. and we can have different types of singularities. That is what we are discussing. So the first point, or like the first type of singularity which we will be discussing, that is the isolated singularity. Isolated singularity. As the name suggests, in the isolated singularity, the point at which the function is not analytic, that is isolated, that is independent of the neighboring points. So I can write something like this. Isolated singularity. A singular point z of f of z for which there exists no neighbors. Okay, so for which there exists a neighborhood, for which there exists neighborhood which contains no singularity. There exists neighborhood points for which there exists neighborhood points which are not singular. Idea is very clear that we have a region. In that region, only one of the point is singular, and all other points surrounding to that singular point are not singular. Then we call that singular point as isolated singularity because it is independent of all other points. All other points are not singular, but only one point is singular.
I didn't understand.
Yeah, with example you will get. Like one example we will discuss, you will get an idea what I am trying to say. One, just I will. Yes. Now let us look at one example. Let us look at. I have a function, a complex function like this. Okay. Now, so definitely this function for this function now this function can be defined for all the complex numbers except for two complex numbers. That is the z is equal to 1 and z is equal to minus 1. Because at z is equal to 1 and minus 1, the function will become non-analytic, and hence z is equal to 1 and z is equal to minus 1 are singular points, singularities, and hence we will call them isolated singularity. Why isolated singularity? Because this function is defined for so many numbers, and among those so many numbers, only two numbers we have for which this function is not like two singularities we have out of so many numbers, and hence these two singularities are isolated singularities because these singularities are not surrounded by some more singularities. They are independent. They are independent of each other. They are not surrounded by more singularities. And hence, it is called as isolated singularity. Z is equal to 1 and Z is equal to minus. So we call Z is equal to 1 and Z is equal to minus 1 as the isolated singularity. Isolated singularity of fx fz. Now we can be more precise mathematically, like what now I will be doing. I will be making a circle. So the same thing we will understand it graphically. I have a circle. Let us suppose this is the center of the circle. And I have a point A. Let us suppose this point A at the center of the circle. Let it be a singular point. Singular point means at this point the function is not defined or the function is not analytic at this point A. Now the idea is that the circle, the circular region around this point A, let us suppose I draw a radius. All these points are analytic. Then I will say that this z is equal to A is a singular point because around the region around the singular point, all other points, they are analytic and hence it's an isolated singular point. And for isolated singular point, one special rule I can remember, the Lorentz series which we studied, it follows a property. Let us we know that Lorentz series is used for expansion of a function around a point. So Lorentz series around the singular point. Very important discussion we are making. Lorentz series around singular point. Here it is A. It can be anything. The question, it can be anything. F of z is equal to. So here for the Lorentz series, the formula which we have discussed, the formula will be same for the Lorentz series, but the interval will be 0 to Z minus A to R. R is the radius. This will be the interval. Like region. Okay.
What does this mean, this expression?
Yeah, we will discuss. See, mod of Z minus A, it represents a circle of radius Z minus A. Now this Z can be any number. The meaning of it I'm trying to explain. The meaning of it says that this thing, this mod of Z, it represents different concentric circles. Now the concentric circles we can have, its radius can vary from 0 to R. If the radius is 0, if the radius of that concentric circle is 0, it means the point itself will be the concentric circle. It can have some more radius. It can have even more radius. The circle will become bigger. The circle can become even more bigger. I'm talking about a region. So the region is the region around A up to a certain limit. That limit is the capital R. So Lorentz series is defined around the point A up to a certain region. And I can, so this mod of Z minus A, it can be any radius between 0 to R. And for different radiuses, we will have different circles. And maximum is the R. In the Lorentz series, we saw now the series is defined for a region, and this is that region. Okay. Now, one more discussion we have to make. In the Lorentz series, we saw that we have two terms, like two series is there in the Lorentz series. If you remember, there were two series. We will discuss that. So the second series, it had V as the coefficient. V1 upon, I will write it down. In the Lorentz series, the portion V1 upon Z minus P plus V2 upon Z minus P plus V3. So we have this portion. We will look at it now itself. Because here we have access to that Lorentz series, which we discussed in the last class. So if you look at the Lorentz series, which we discussed, we saw now that Lorentz series is, we calculate round up point. So there is a region defined, and the region is defined based on these concentric circles. So for all Z belonging in R, at Z is equal to A. So this point A and a region, this Lorentz series is defined. So we are expanding the function fz at a point A in a region R. And this expansion is this. The formula, the red pen, A naught plus A1, something. We saw it has two terms, like two series it has. It is the first series, it is the second series. The first series is z minus a to the positive power, like 1, 2, 3 and all. And in the second series, z minus a to the negative power. And we have terms like this, v1 upon z minus a plus v2 upon z minus a square and so on. Now see, when we are talking about singularity, because around the point A, if I am expanding the function, this is the formula which I will get, the series formula. Here in this series, here I have no concern. It's fine. No singularity, nothing. But here I have a concern because here I know that at z is equal to a, function is not defined. At z is equal to minus a, like a, the function is not. So here we can focus a bit more. And that is what we are trying to focus when we are discussing singularity. Isn't it?
Yes.
So Lorentz series for a singular point, like here a is the singular point, it means at a the function is not defined, the function is not analytic. And we can see from the second portion itself, we can clearly say that okay, at a the function is not analytic at all. And this portion of the Lorentz series is known as, is given a special name, and that special name is the principal part of fz. I will write it. So this thing which we get, this we call it as the principal part of fz. Very principal part of fz at z is equal to a. Now it is very clear to us that we have given a function, we know a singular point of it. We have to find the principal of part of that function around that singular point. Let us make the Lorentz series, and the second series inside the Lorentz series containing the z minus a negative powers. That portion is the principal part of fz at z is equal to a at any singular point. And one more terminology we should be aware of. Here, this coefficient B1, the coefficient B1, it is given a special name. It is called as residue. It's called as residue. Residue of the function. Residue of fz. Residue of fz at z is equal to a. At z is equal. Now this is the concept of singularity, like isolated singularity. Now here one more concept we can discuss. The concept of pole. What is pole? Okay. So the idea is that if the principal part, if the principal part of function, principal part of fz, the function at any singular point z is equal to a is finite. Is finite. The principal part is finite. Then we call the principal part as the pole. Okay, so not principal part, the singular part. Okay. Singular point. Z is equal to A is called the pole. Is called the pole of order n. Order m, with the example, we will get the meaning of order m. I will like prove it, like demonstrate what is order very soon. X. Now we will look at some example to get an idea. Before that, one more point we will discuss, then we will straight away jump into example and you will get a very good clarity. Like whatever we discuss, it will make sense to you. If the order is 1, then the pole is simple pole. So simple pole is a pole of order 1. Okay. Now let us look at some example to get more clarity. Like whatever we discuss, it will start making sense with these examples. Let us suppose I have a function, complex function like this, z upon z minus 1, z plus 1 to the power of 3. Now can you tell me these singular points for this function?
So 1 and minus 1.
1 and that is. So z is equal to 1 and z is equal to. Now here one more very interesting thing we can see that since it is of the form of b upon z minus 1 to the power of n. So these points are the pole. Why it is the pole? Because this we have a finite series here, like it is finite, and we have something of this form, and hence the singular points 1 and minus 1 can be called as the pole. So now it is very clear to you in the question, if we have been given a function and it is been asked Okay, identify the poles. So you can very easily see that, okay, it is 1 of like b upon z minus 1 or z minus a to the power of n, to be more precise something. If it is of this form, we can say that, okay, these singular points which we will get from this equation, that will be the pole itself. So z minus 1, it is a pole. It's a pole of order 1 because here the power is 1. It is a simple pole because pole of order 1. Pole of order 1 is called as the simple pole. It's a simple pole. And z is equal to minus 1. It is a pole of order minus 1. The pole of order.
Pole of order 3 over there.
Oh, sorry, sir. I'm extremely sorry. You are right. It's a pole of order 3. Because power we have to look and power is 3. That is right. It's a pole of order 3. Now let us look at some more examples related to poles to get a more to get some more clarity. So I have a question. Find the poles find the poles for f of z is equal to e to the power of z. Now see, this is the question. So a function is given and we have to calculate the poles for this function. So looking at this function, though, we cannot see any singular point because this function seems to be analytic at all the points. This function is always defined. Now, what I can do is to take our analysis one step forward. E to the power of x, this function I can expand. So e to the power of z, I can expand it. And when I will expand it, because it's a very famous series, 1 plus z upon 1 factorial plus z square upon 2 factorial and so on. Now, after expansion also, we can see that this function is analytic at all the points. There is no singularity we can identify. And since no singularity is there, no pole exists. So the answer is no poles. Why? Because this function is analytic everywhere. I can write since this function is analytic everywhere, in capital C, that is a set of complex numbers, no pole exists. No pole exists for f of z. Now let us look at some more questions to get an idea. Find the poles for f of z is equal to e to the power of 1 by z. Okay. This is the function, and once again we can expand it using the series formula. It will become 1 upon 1 by z, because the same thing, the same formula we are applying. 1 by z, I am treating it as z or x, and I know now the series formula. Let me write it for reference. I am writing e to the power of x. We can expand it. A very important series formula I have. 1 plus x upon 1 factorial plus x square upon 2 factorial plus x cube upon 3. So this formula you remember, and it is an infinite series. It will go up to infinity.
Yes, sir.
Okay.
So we are writing for the model of z.
Yeah. So same is applicable for z. And now here we have 1 by z. So instead of x, I can write 1 by z. So it will become 1 by z, 1 factorial, which will be 1 itself, plus 1 by z square, 2 factorial, plus 1 by z cube, 3 factorial, and so on up to infinity. Now looking at this, definitely we can identify the singular point. So what is that singular point which we can identify?
Zero.
0. 0 is the singular point. So at z is equal to 0, the function is not analytic. So we found the singular point. But if we talk about the pole, for the pole, one very important condition is that this series, it should be finite. But here the series is infinite, because exponential series by default it is infinite, and hence no pole exists. So we can say that here principal part, this 1 upon z minus a to the power of n, we are calling it as a principal part. So here principal part of f of z contains infinite series. Contains infinite series. So we can say that no pole exists. No pole exists.
So I have written that here the singularity of fz is zero, but it is an infinite series. And as we know that the pole should contain finite series, and there is no pole exists, because fz is equal to e to the power 1 upon z.
Okay, so
Is
see,
correct?
to be more precise, it is right. It is right. You can say that here z is equal to 0 is the singular point. That's fine. But write it like this, so that in just two statements, you are concluding your answer. Like here, because the definition of pole is that principal part of the function should be finite. So here we are specifying that only here principal part of fz contains infinite series or infinite terms. So no pole exists for fz is equal to e to the power of 1 by z. So you can keep it simple like this also. Next question we can look at. Find the pole of f. Find the pole for fz is equal to z minus 2 plus 1 upon z. So here very clearly we can see the principal part also. So singularity to you can very easily identify, and we can see that singularity is taking the form also of the principal part of the function, and the principal part is finite also. So we can say that z, I can write it, z is equal to 2. It is the pole of the function. And what is the order of the pole of the function? Pole 1. Pole of fz of order 1. So it's a simple pole. When order is 1, it's a simple pole. It's a simple. One more question you can have. Find the pole for f of z is equal to 1 by z square minus 1 by 2 factorial plus z square by 4 factorial. Minus and so on. Now give it
So
a
there
try.
will be no pole, right?
Why?
So because it's like so on.
So on in
Infinite
infinite series. Yeah, that is what I was expecting from you. Like we make mistakes like this, and you
But
have
it's
made
not
one
the
mistake.
answer.
Yeah, so try to check why there will be a pole. Pole will exist despite the series is infinite. Despite the series is infinite, there will be a pole. And very simple explanation, and you will agree that it's right. Because infinite series, here you have to focus on principal part. And what is principal part? 1 upon z minus a to the power of n. Now the idea is that all these terms, they will not contain any principal part, because z square, then z to the power of n.
So it's not in the proper series.
Yeah, no. So these terms, they will never contain z in the denominator. And hence, this will not be the principal part. Principal part, it is having only one term.
So, but in EZ also there was no Z in the denominator. Then also it was no poles. Because in EZ, the function was analytic everywhere. So in EZ, there is no singularity, and without singularity, the pole is impossible. In EZ, singularity does not exist. The function is analytic everywhere. So no point of having the pole. Because see, pole, what is pole? Pole is a special type of singularity in which the principal part is finite, isn't it? Not getting. Yes, sir.
Here, in EZ, the function is defined for all the points. The function is analytic everywhere. So no singularity exists, and hence no pole. But here, we have a principal region, a principal part of the function is available, which is this, only one term. And we can say that at z is equal to 0, the function is not analytic. So z is equal to 0 is the pole of this function of order 2. The square is there. So we have a pole of order 2, and that is z is equal to 0. Isn't it?
Yes, sir.
So here I can say that z is equal to 0 is the pole of f of order 2. So this was all about isolated singularity. Until now, we were discussing the isolated singularity, in which we saw that isolated singularity means we have a singularity surrounding it, there is no other singularity. And we saw one very important property of isolated singularity, that the Lorentz series around that isolated singularity, the second series containing 1 upon z minus a to the power of n, that is the principal part of the function at z is equal to a, and based on that principal part, we gave the definition of the pole. If the principal part is finite, then we say that that singularity is the, that we call as the pole of order n. And in this way, we did some questions of the pole also to get a clarity. Now we will discuss the second type of singularity, that is the essential singularity. Let us discuss that. Second type of singularity. essential singularity. So this is very, now it will be very easy to understand. Essential singularity, the idea is very simple. If principal part of fz principal part of fz at z is equal to a, like z is equal to a is a singular point. So if the singular point, its principal part is infinite, contains an infinite terms, then we say that, then we say z is equal to a is called the essential singularity of f. Okay. One example we can take, the same example, one of the example which we discussed, wherein we were getting infinite, hence we had to say that it is not a pole, but now we can say that it is a essential singularity. So the example is something like this. We have a function f of z is equal to e to the power of 1 by z. And if we do the series expansion, I know that it's 1 upon 1 by z, 1 factorial, one by z square, 2 factorial, and so on. Now definitely z is equal to 0 is the singular point. And since this principal part of the function is infinite, I can say that z is equal to 0 is the essential singularity. Z is equal to 0 is an essential singularity. Is an essential singularity of f of z. Essential singularity is also clear. Now the third type of singularity which we have, that is the removable singularity. removable. Singular. Let us see what it is. It is very interesting that if the principal part of the function, if the principal part of the if the principal part of function f of z contains no terms. Like if the principal part does not contain any term, if the principal part of f of z contains no terms, it can happen. Then singular point z is equal to a is called removable. Singularity of f of z. So this is the idea. So here the function, it will only the Laurent series of the function, it will have only the first series, like 1 upon z minus a to the power of n. That series is not present. So here f of z will take a form like this. Summation of n is equal to 0 to infinity an z minus a to the power of. Let us look at one example, get more clarity. I have a function f of z is equal to 1 minus cos z by z. Now looking at it, you can say that okay, z is equal to 0 is a singularity, a singular point. Because at z is equal to 0, the function is not analytic.
Okay.
But we shouldn't be in so much hurry. Because this function, we can make it analytic everywhere. How we can do that, I will show you. So we have to do some simplification. F of z, it will become 1 by z I can take outside, 1 minus cos z. Now I can use the series expansion of the cos. I can write it here for the reference. For cos x it is equal to 1 minus x square by 2 factorial plus x to the power of 4 by 4 factorial minus x to the power of 6 by 6 factorial. So these all you have to remember, like series expansion of sin x, cos x, and exponential and logarithm. So if I apply that, I will get 1 minus z square by 2 factorial plus z to the power of 4 by 4 factorial minus z to the power of 6 by 6 factorial and so on. Now I can simplify it further. So this plus 1 minus 1 will cancel and minus it will come get inside, it will make it plus. So z cancel. So I will get z by 2 factorial. And the next term will be minus z cube by 4 factorial. Next term will be plus z to the power of 5 by 6 factorial. And so on. And it will keep on going infinity. And as you can see, after simplification, we saw that there is no z in the denominator. And hence, this function is analytic everywhere. So what I can say is z is equal to 0 is the removable singularity. Looking at z is equal to 0, it is looking, it was looking that okay, it is a singularity, but it can be removed, and we removed it. So I can say that z is equal to 0 is a removable singularity. Of f of, okay. So this concept is clear. So singularity, all the types of singularity we completed. Now we can look at one more concept, that is the concept of residues. Let us discuss that. Let us discuss somewhere here itself. Calculus of residues. calculus of residues. So now we will learn how to calculate the residue of a function at singular point or at z is equal to a, any point z. So let us write evaluating residue of a function or residue of f of z at z is equal to a. So two scenarios we have to discuss. The first scenario is the one wherein z is equal to a is a pole. Simple pole. Simple pole means order of one. Let us suppose z is equal to a is a simple pole. We have a function wherein z is equal to a is a simple pole. First, we will discuss this. In this scenario, how to calculate the residue. In this scenario, the Lorentz series of fz it will be equal to see what is the definition of the pole. Definition of the pole is that the Lorentz series, the principal part, it should be finite. It means the Lorentz series, it should contain both the parts and the principal part should be finite. So I can write like this. It should contain both the parts. So let us suppose the first part I can write like this. Summation of n is equal to 0 to. So the first part of the series, it can be infinite. It's fine. The first part of the series with the coefficient a and z to the power of positive n. But the second part has to be finite as per the definition of the pole. And if it is a simple pole, then it should have only one power. That's it. So if z is equal to a is a simple pole, then the function will be having this form. The Lorentz series of the function will be having this format. And here, the B1 coefficient is the residue, and that is basically formula is there for that. 1 upon 2 pi I integration of the second circle integrating the function f omega upon omega minus a minus 1 plus du. It will be, finally I can write it, 1 upon 2 pi I integrating fw dv, because it will become 1 denominator, it will become fw. Now this is the equation 1 which we have. In this equation 1, this I can write in the bracket. The b1 is this. This is the main equation, equation 1. In the equation 1, I have a b1 term. The value of that term is this, 1 upon 2 pi I integration fw dw. Now what I will do, I will multiply both the sides of the equation 1 with z minus a. Multiplying both sides of equation 1 with z minus. Then we will get something like this. Emphasizing. I will get something like this. Z minus a f of z is equal to the first term. It will become z minus a n to the power of plus 1. Summation of n is equal to 0 to infinity a to the power of n z minus a to the power of n plus. And here z minus a will cancel, and we will be having b1. Now what I will do, I will take limit on both the sides. Taking limit z tending towards to a on both sides. Now when I will take the limit, I will get something like this. Limit z is tending towards to a, z minus a f of z is equal to, and here when z will tend towards a, uh, so z will become approximately a, and a minus a will be 0. So I can write it 0 because it is infinite now. When the series is infinite, definitely at any point it will touch z is equal to a. And this I can take it as b1 itself. And I know that b1 is the residue that we have already seen.
V1 is the sir?
Residue that we have seen here in singularity. Here b1 is the residue. This line. So b1 is the first coefficient. So first coefficient is always the residue. The first coefficient of the principal part of fz, that is the residue. And here the first coefficient of the principal part is b1, and hence b1 is the residue. And this b1 is this value we calculated. So I can say that b1 is equal to limit z tending towards a z minus a fz. This is the simple residue. Is the residue of the function fz at a simple pole. At a simple pole, z is equal to a. So if the simple pole is given, then and if they are asking residue, you just have to remember this formula. Now the second condition we will discuss. Second condition. Suppose z is equal to a is a pole of order n. Is a pole of order n. Same calculation we can do, just order we have to change it to n. Then our Lorentz series, it will take this form. Lorentz series of f of z, it will become something like this. Summation of n is equal to 0 to infinity a to the power, like a base n, like subscript, z minus a to the power of n plus. Now this principal part has to be finite, because if there is a pole existing, it has to be finite. It will be finite plus b2 z minus a square, and it will go up to bn z minus n, yeah, z minus a to the power of n, because n is the order of the pole. So this is the equation we got. We can call it equation 1. Now I will be doing the same, multiplying both the sides. Multiplying both sides of 1 with z minus a to the power of n. Z minus a to the power. I will get something like this. Z minus a to the power of n f of z is equal to summation of n is equal to 0 to infinity a n z minus a. If I so the base will become 2n, n plus n, plus it will become b1 z minus a to the power of n minus 1 plus b2 z minus a to the power of n minus 2. Isn't it?
Yes, sir.
bn, and this will cancel out.
So which will cancel out?
The last term, because if, in the denominator we have z minus a to the power of n, and we are multiplying it with z minus a to the power of n, it will cancel out. So we will only have bn, isn't it? Now what we have to do? Now basically we have to differentiate differentiate. So this is the equation 2 which we got. I can write it equation 2. So differentiate equation 2 n minus 1 times with respect to z, and then take limit z tending towards a on both sides. Let us do this. So ultimately, we have to differentiate it n minus 1 times. I can write it something like this. Just one. D n minus 1 by dz n minus 1. And we have to differentiate this entire thing, that is z minus a to the power of n and f of z. and I have to take the limit also. Limit z is tending towards a, isn't it?
Yes.
Now, on the right hand side, when I differentiate it with respect to n minus 1, and when I take the limit, z is, so the first term of the series, it will vanish because of the limit. And for the second term, what I will be left with is b1 n minus 1 factorial. This I. So the residue, what I will get is this formula you have to remember. B1 is the residue. So B1 is equal to 1 upon n minus 1 factorial. Limit z is tending towards a, differentiating this function with respect to z n minus 1 times. We have to differentiate n minus 1 times, isn't it? Then z minus a to the power of n. And finally, f of z. This is the formula. This is the formula for the residue. So I can say that the residue of fz at pole z is equal to a of order n. So two formulas you have to be aware of. That's it. If the order is 1, simple pole, then this is the formula. This is a simple formula. And if the order n pole, then it's a bit complex formula. Now, if we look at some questions, it will be very clear to us like what is happening. We will get an idea. Question, let me write it. The question they are asking, find the poles. Find the poles and the corresponding residue at each pole. Okay. So here the function, let me write it. So function is f of z is equal to z plus 1 upon z square z minus
That's where bracket.
z minus 2. Okay. So first identify the pole and then the residue.
The pole will be 0.
Yeah, very nice. So first let me write the poles. Z is equal to 0. Z is equal. So is Z is equal to 0 a simple pole? No, order 2. And Z is equal to 2 is a simple pole, isn't it? Z is equal to 2 is a simple pole, order 1. And Z is equal to 0.
Order 1.
Yeah, simple means order 1. And Z is equal to 0. It is a pole of order 2, isn't
Order
it?
2.
Yeah. Now we have to calculate the residue. Let us do that. So first let us calculate residue. At Z is equal to 2, simple pole. And we are aware of the formula. Formula is limit Z tending towards 2, Z minus A to Z minus 2, f of Z. So f of Z we can substitute from the given function. So Z minus 2 will cancel. It will give us limit Z tending towards 2. Okay, let me write one more step. Z minus 2 and f of Z I can bring it from the question itself is given Z square Z. Now this Z minus 2 will cancel.
Yes, sir. It will be Z plus 1 upon Z square.
And this limit I can just substitute 2. So 3 by 4. Isn't it? Instead of Z, if I substitute 2, I will get 3 by 4. And this is the answer. Similarly, I can calculate the residue at the other point. Z is equal to 0. What it will be?
Yes, I do.
It will be 1 upon Z factor. Like what was the formula? N minus 1 factorial. And N is the order. And here the order is 2. So 2 minus 1. Sorry?
So इसमें दूसरा फॉर्मूला लगेगा.
Because order is 2 now. When order is 2, दूसरा formula है. For order n, let me show. So this
इसको
formula,
डायरेक्ट कैसे लिखा है? 2 minus 1 continue.
yeah, this formula we have to use for order n. So
Which
n
one?
minus 1 factorial. This one, the formula which I have highlighted. This is the formula for any order other than 1. For any order n, this is the formula. If the order is 2, 3, 4, 5, you have to use this formula. So 1 upon n minus 1 factorial, where n is the order. Limit z tending towards a. A is the singular point or the pole. And we have to differentiate it n minus 1 times. Z minus a to the power of n fz. And this same formula we are applying here. If you want, I can copy this formula. Just come here. So that you get more clarity what we are doing. So this is the formula, okay? Now let us apply
Yes.
it. Let us apply it. The residue we will get is 1 upon n is 2 order 2 minus 1 factorial. Limit z tending towards 0
Yes.
d to the power of 2 minus 1
2 minus 1.
upon dz 2 minus 1. In the bracket z minus 0 to the power of 2 f of z.
And fz.
I can write f of z. I can take it z plus 1 z square z minus 2. Isn't it?
Yes, sir.
It will become 1 limit z tending towards 0, and I have to differentiate it one time with respect to z, d by dz. And here square will cancel, z square will cancel. I will be left with z plus 1 upon z minus 2. And here, when I will differentiate it, the quotient, the remainder that d by dx of x by y, fx by gx, something like that. If you remember the differentiation of such formula, so it will be something like this. I will write it. I will write the formula also. Limit it will be first function, like differentiation of first function into second function, plus second function into different first function into differentiation of second function. So minus. So it will be upon denominator square.
We have to differentiate it, sir.
Differential. I will tell you the formula which I have used. D by dx of fx by gx. Isn't it?
Yes, sir, but we have to differentiate z minus
So
2
yeah, so
and
it
then
is
integrate.
differentiation of first function into second function minus first function into differentiation of second upon second function का whole square.
Yes, sir.
That is what.
You
Now
directly written the answer.
I have directly differentiated. So this is the z plus 1 is the first function, z minus 2 is the second function. So I will get this. And when I will substitute the limit, then I will get 0, I
The
will
first
put
function,
z plus 1.
plus 1, right?
Yeah. So differentiation of first function is 1. So 1 into z minus 2 minus differentiation of second function is 1. So z plus 1 into second differentiation of second function upon z minus 2 ka whole square. When I will put 0, I will get minus 3 by 4. This is the answer. Getting it?
Yes, sir.
Isn't it? Now, one more question let us do. Like, now it will be easy for you. Find poles. And corresponding residues at each pole. Function is given. This is the function. Now, first let us analyze the poles. So it has only one pole, that is z is equal to 0 and order 4. And its residue we can calculate, because if order is 4, the second formula will be used for the residue. Isn't it? Let us look at the formula. This is the formula. Now I can just plug in the values to get the answer. The residue will be n is 4. So 1 by 3 factorial limit z is tending towards 0. Okay, b n minus. Here also let me make the correction. N minus. So it will be D3 upon dz in the bracket z cube okay, z to the power of 4.
So it will be 1 minus Ez upon E square. E cut diagonal.
Okay, let us see.
It will be minus Ez measures. 1 minus Ez.
1/6. So z4 will cancel. 3 times if I differentiate it. So first time I will get minus Ez, then plus Ez, then minus Ez. E to the power of 0 is 1. So minus 1/6 will be the answer. So minus 1/6 will be the residue.